Okay, let's get started. So, quick question. How many of you have gone on YouTube and listened to me lecture on this lecture? One. Okay, that's good. So I'll disappoint you, not much has changed. But really this lecture is just kind of meant to set the foundation for kind of what we're going to be talking about for the next 10, 11 days. I'm sure much of it will be quite elementary on some level, but I think it also is informative in the sense that it kind of will set the stage for the framework in which we kind of think about the field of multi-scale biophotonics. And I have about a little less than 50 slides, and I have about 90 minutes. I want this to be conversational. In some sense, this lecture really kind of scrapes the surface, but it's like peeling an onion. There's a lot of depth to all of the topics that I'll be covering. In a cursory manner here, and we'll be revisiting these topics as the course goes forward. But please, if you don't understand something or you have a question that's pertains to your particular research or ideas you have with respect to modeling, computation, experimentation, whatever, please, this is kind of what the whole course is about, to learn from each other. So I'm just going to lay out kind of the teaching objectives. The title of this program is Multi-Scale Biophotonics, and that implies temporal and spatial scales. And biophotonics encompasses a broad spectrum of techniques, going all the way from probing biological cells and tissues on the hundreds of nanometer spatial scale, with linear and nonlinear microscopy techniques, all the way to diffuse optics, where you're actually probing centimeter type volumes, right? And a key element for all biophotonic applications are, number one, either sensing light that has been that is remitted from the tissue, or in the case of therapies, or even in the case of fluorescence, generating a light field inside the tissue, which will then generate light that you can sense. So we need to have approaches for understanding that light transport and for modeling light propagation in tissues across these spatial scales, from the nanometer spatial scale all the way to centimeters. And depending on your application, the approach that you take is informed greatly by the spatial scales that you're considering. The other thing we're very concerned about is whether your objective is therapy or diagnostics. And given one or the other, what you want out of your light transport model is different. Therapy, you're very interested in understanding what is the volumetric distribution of the light. In diagnostics or in imaging, you are only interested in sensing the light coming out. And for the most part, that is, you're just interested in the light field on the surface, right? Unless you're going to stick an interstitial probe to get some information on light. So understanding the interplay between those two is important, and we'll talk about how they're related. Now, on the micro scale and nanoscale, the only rigorous way to model light transport is doing a rigorous Maxwell's equations solver. And we'll talk about that a little bit, but really it's quite impractical in most cases, although research is ongoing in that area. If you look at the field of biophotonics in the whole from a modeling computation perspective, things are done in what's called the radiative transport context. In that context, you treat light not as waves, but as neutral particles. And you don't treat light in terms of electric and magnetic fields, but you treat light in terms of what's called radiance. And radiance is something that even in the diffuse optics field, people don't emphasize it enough. You may be more familiar with terms like fluence and fluence rate and flux, but ultimately all of those quantities are derived from the radiance. And so we're going to talk about the radiance. It's a 6-dimensional object. that's parameterized with time, space, and angle. So you got 1 dimension of time, 3 dimensions of space, and 2 dimensions of angle. So that's 6 dimensions. And it can be quite daunting. It was for me, at least, when I first tried to wrap my head around that. So that's roughly the first, and then once we define what the radiance is, we'll talk about how we treat light transport and how it's modified by absorption in the tissue, scattering the tissue, and how combining the effects of absorption and scattering lead to what's called the radiative transport equation, which is kind of the foundation of diffuse optics. And that's precisely the equation that Monte Carlo simulations solve, is the radiative transport equation. So then we'll leave kind of modeling behind. That'll be roughly the first half of the lecture or so. And then we'll talk about optical properties, because obviously to solve or to understand light transport, it's all governed ultimately by the optical properties of the tissue. We're going to talk a little bit about where those properties come from, what are their characteristics, what is the dependence on wavelength, etc. And then once we understand kind of the process by which light propagation occurs through the RTE, and we understand optical properties, that combination naturally gives rise to characteristic spatial and temporal scales. And you will find that those temporal and spatial scales actually have direct bearing on, come about. You see them again when considering the spatial and temporal scales of which various biomedical optics technologies operate. And so, you've heard, many of you, of spatial frequency domain or temporal frequency domain imaging. And so the spatial and temporal scales that these systems are designed to probe tissue, those spatial and temporal scales come directly from a combination of tissue optical properties and essentially the speed of light in tissue. So we'll talk about that and how to calculate it. Okay, so just, high school physics, we can treat light either as a wave or a particle. In the wave context, light is essentially a transverse electromagnetic wave where the direction of propagation is mutually orthogonal to both the electric and magnetic field oscillations, right? And that the spatial scale of light, the wavelength of light, is essentially the physical distance between two peaks or two troughs in those electromagnetic oscillations. And of course, as I just mentioned, sometimes we don't deal with the full wave character of the light, although it is certainly leveraged. Obviously in microscopy, in OCT, in speckle imaging, we are leveraging intrinsic qualities of the wave nature of light. But in diffuse optics, spatial frequency domain imaging, diffuse optics, we don't leverage the wave properties of light, but really adopt a description where the wave properties of light have really been scrambled, destroyed by the multiple light scattering in tissue, and we can treat light transfer as a neutral particle and known as photon. So photons are localized. There's a massless quanta of energy, and actually they carry momentum, which gives the ability for us to use optical tweezers. And the relationship between the energy of a single photon is linked to the oscillation frequency of light, nu, and multiplied by Planck's constant. And there's a relationship between frequency of light, nu, and the wavelength. So nu is c over lambda. So essentially, the higher the wavelength of light you utilize, the lower the individual photon energy is. So this next slide just is meant to illustrate, that we tend to focus on this very narrow sliver of the electromagnetic spectrum, kind of from the ultraviolet to now into the near infrared or even shortwave infrared. But certainly there are other forms of light that can be used for biomedical optics applications. Some of you may have heard of terahertz imaging. Certainly people here know about X-rays. And what's interesting about considering these forms of radiation is to think about the spatial scale of the oscillations, electromagnetic oscillations, and comparing that to the spatial structures in biological systems that you're interested in probing. And what's really interesting about the wavelengths of light that we tend to use in biomedical optics is that we tend to use light on the order of a few hundreds of nanometers to maybe out to a couple microns. And what's interesting is that in biological systems, that's where a lot of the action is happening, right? If you think about subcellular structures, organelles, are on the spatial scale of tens to hundreds of nanometers out to microns, right? And so in fact, you are vibrating in an electromagnetic wave frequencies that are resonant in some sense to the structures in cells and tissues. The other way to think about it is from an energetic perspective. So often the energy of photons are characterized by electron volts. There's a simple way you can calculate electron volt energy relative to wavelength. But if you look at energies in the visible, from the near infrared down to the ultraviolet, I've got to turn on my screen saver at some point, you find that these energies are in the same domain as either vibrating, the vibrational states of biomolecules. So in the near infrared, what gives rise to absorption of light in the near infrared is that you're basically exciting vibrations in the biomolecules. And then as you go to the visible and UV, you are able to excite electrons from a ground state to a higher excited state. And that sometimes also gives rise to fluorescence, right? So essentially, the fluorescence emission you see is because you've used UV or visible or sometimes high intensity near infrared light to promote electrons to a higher energy state. And then when they decay, they release light. So fluorescence is actually the decay of electrons from a higher energy level back to a ground state. So using light across a spectral band gives you the ability to probe the electronic and vibrational transitions of biomolecules. If you go to terahertz, you're actually starting to probe rotational transitions of biomolecules. And then if you go into X-rays, you actually go through the whole electron cloud and you're probing the nucleus. Okay, so that's kind of gives you kind of where we stand in biomedical optics and the value it has. So now let's talk about spatial scales, right? So as I already alluded to, the range of applications in biomedical optics go from the nanoscale, from even bright field phase contrast microscopy to now very elegant, nonlinear coherent-based imaging techniques. Of course, multiphoton microscopy has now been around for a while. Second harmonic generation, some frequency generation, coherent Annie-Stokes-Raman. They're just a panoply of really impressive nonlinear coherent-based microscopy techniques, that all of which are able to probe specific structures and compositions within tissue. And so they really utilize the coherent wave nature of light, the ability to excite emission from either native biomolecules or from contrast agents that are intentionally put in tissues. But ultimately, you're able to create light fields on the sub-micron spatial scale and either understand how that light is modified by the tissue and re-emitted, or you're able to excite nonlinear signals, linear or nonlinear signals within the focal volume, leading to the emission of light at different wavelengths, but it gives you some indication of the intrinsic composition or structure of the tissue. And then if you are willing for the light to propagate through your sample over microscale distances, you can start to probe structure or flow of biological samples. OCT is intrinsically, the contrast comes about from scattering of the tissue, changes in polarization, because as you know, many tissue structures are, let me get out of here and turn off my screensaver. Apologies for that. Let's try this. So you allow light to propagate on the tens to hundreds of microns, but ultimately you're still leveraging the wave nature of light, the coherent nature of light, the ability of light to lose coherence, or the ability of light to interfere with itself due to multiple scattering. So even though you have single or even multiple scattering, you're still leveraging contrast that's linked to either structure or flow in the tissue, and the fact that the light can still retains some coherence so that you can visualize interference or diffraction. So and then if you let light propagate even further, the light scrambles such that it no longer has a coherent wavefront, and you lose the ability of light to undergo interference or diffraction. You kind of go into a diffuse haze. So you kind of transition from this wave nature and this transport nature of light into the diffuse character of light. And techniques such as SFDI and diffuse optical spectroscopy imaging really operate in what's called this transport and diffuse domain of light propagation, where we can use radio transport and treat light as a particle. And so in terms of a modeling framework to understand this, as I've already alluded to, when you're using or leveraging intrinsic wave characteristics of light, one must do a Maxwell's equation treatment of this phenomenon. And so when you're on spatial scales on, I would say even tens or even hundreds of wavelength of light, in terms of spatial scale, you really need to treat Maxwell's equations. Now, if you let the light propagate and you lose the wave character of light, you can now treat light as a photon, and you can adopt the radiative transport context. Here, the fundamental spatial scale is known as the single scattering length. We call it L sub s. It is the characteristics distance that a photon can travel within the tissue before it encounters a scattering. And in the kind of visible near infrared portion of the spectrum, that spatial scale is anywhere from, say, 5 to 50 microns. That's the characteristic time that light can propagate before undergoing the scattering event. Here, here you can treat that propagation over spatial scales larger than LS using radiative transport. Now, if you let light propagate further and further on, what happens is that even though you've lost the coherent nature of light, ultimately it loses memory of the initial direction. So we often initial direction of propagation. So often we use collimated sources of light using lasers, right? So it has a very strong initial direction. You can lose the wave character of light, meaning the wavefront is gone, but you can still have some directional character. But ultimately, if you undergo enough scattering events, there's no correlation between the direction of light propagation and the initial direction. And the spatial scale over which there's a loss of correlation between the initial direction of propagation and the current direction of propagation is called the transport mean free path. So in the diffuse optics literature, you probably have seen this, and it's usually denoted as L star. And so when you're on spatial scales of larger than L star, you can now utilize an approximate solution to the radiative transport equation, because even though this equation is simpler than the Maxwell's equations to solve, it's still very difficult to solve, and that's why we use Monte Carlo simulations to do it, to solve it. But if you're able to if you're on a spatial scale where this directionality is lost, you can actually reduce this to the diffusion approximation, which is actually fairly simple to solve. You can integrate that, and you can incorporate that into any kind of finite element or finite difference solver you might use, like COMSOL, for instance. It's very easy to implement. So, oh, Richard has overtaken my interest.
Are you still in Zoom?
I am. From my note. USB sharing is okay.
You're back.
Okay. Okay, so I'm going to kind of dig a little deeper. So Maxwell's equations, provide a rigorous classical model for EM wave propagation. It models all wave phenomenon, interference, diffraction, polarization. It's accurate across all spatial scales. If we had the ability to utilize Maxwell's equation, it is, in some sense, the gold standard. Go back to full screen. Okay, there we go. Now, the challenge with utilizing it are twofold. Number one, the intrinsic properties that you need to know about the material in order to solve Maxwell's equation are two things known as the dielectric permeability and the dielectric permittivity. They basically tell you to what degree the material can sustain electric field oscillations and magnetic field oscillations. Now, knowing these values or obtaining these values in tissue systems is very difficult, and they're often unknown. And the other thing, as I alluded to, the modeling of propagation, wave propagation in scattering media is very computationally expensive. But many have applied it to small tissue volumes. And when I talk about small tissue volumes, I mean tissue volumes on the order of, say, 100 micron. Even then, solving these equations on that sorts of volume still takes about thousands of hours of computational time on supercomputers. But it's proving to be valuable to understand the distortions that focus beams of light that are often used in microscopy undergo when they encounter tissue scattering. And there also been advances by our group and other groups, Buddy Bachman in Northwestern, Andy Dunn at UT Austin, that are kind of pushing the forefront of the applications of Maxwell's equations in biological media. So, as I've already said, if you're no longer interested in the wave character of light, you can you can model the transport phenomenon using the radiative transport equation. Treats light propagation as transport of photons, neutral particles. And interestingly, in the last, I would say 15 years or so, they've been able to actually derive the radiative transport equation from Maxwell's equations as a limiting case of Maxwell's equations when certain conditions are satisfied. And I haven't listed all of the conditions, there's several, and I've given you references in that reference sheet. If you want to probe this issue, we'll roll further, and I can certainly chat with you. But the two key assumptions are that particles are the things in the tissue that give rise to scattering. And to get to the radiative transfer equation from Maxwell's equations, we must assume that each scattering particle in the tissue lies in the far field of scattered waves produced by other particles. So what happens is that you have, say, a plane wave that's incident on a particle, and then you get a scattered wave that's emitted by that particle due to light scattering. Now, it turns out that if you look at the scattered wave very close to the particle, it's actually evolving with distance. The angular distribution and amplitude volume with distance, that's called the near field. And then ultimately, once it propagates about 5 to 10 times the diameter of the particle, you get a spherical wave that no longer evolves. So long as your particles are situated far enough apart such that no particle lies in the near field of other particles, you can adopt the RTE. So that's what it says here. The other thing is that the RTE treats the medium as a random medium. that there's no correlation between the locations of scatterers in your media. Because what can happen is that if there are correlations, spatial correlations in where the particles reside, then you can actually set up situations where you have constructive interference in one direction and destructive interference in other directions. And so you have to assume that there's no spatial structure that's uniform in any sense. So there should be no correlations between particle positions. The other thing I would add is that if the light field that you are interested in modeling is sensitive to the locations of the particles, then RT is not for you. You have to go to Maxwell's equations. Okay? So you have to actually not care about where the precise positions of the particles are. So you can actually be on larger spatial scales than the wavelength, on tens or hundreds of microns. But if the light field that you're interested in modeling is dependent on the specific